Hi everyone, so this video lecture is going to cover the Reynolds number and how it can explain pipe flow and the behavior of the fluid within the pipe. So the Reynolds number is a non-dimensional number that relates the diameter of the pipe, the velocity of the fluid within, the viscosity of the fluid, and the density that the fluid flows at. So friction in pipes does depend on the velocity of the fluid. The faster a fluid moves within the pipe, the more friction is going to be created. And this friction then impacts the amount of heat transfer that can occur within the fluid as it flows through the pipe. So a way to monitor this and measure this is by using the Reynolds number. And as you can see on the graph here, as far as the velocity increases, so the change in pressure over the length of the pipe. So if it moves from one end of the pipe to another over a certain length, the higher the pressure drop is going to be impacted by also the velocity of the fluid going through the pipe. And this is related to the flow rate, the volumetric flow rate of the pipe. And the first relationship of these numbers is pretty linear and straight, and this is going to be the laminar flow regime, which we'll get into later. But this is where the velocity is lower and viscosity is the bigger factor as far as the behavior of the fluid. As you move up on the graph, there is a transitional region where the flow is unpredictable. There is not as much there isn't a steady flow of pipe, but it also isn't tumbling back on itself either, which is what happens here as the relationship becomes more of a quadratic function. So here, the fluid will start to create eddies within it, and instead of being a straight line, it will swirl on top of itself. This is going to be the turbulent flow region. The Reynolds number can relate laminar flow and turbulent flow and differentiate between the two of those for different types of fluids. So as explained, for lower flow rates will be the laminar regime. The intermediate flow rates alternate between the laminar and the turbulent regime, and that will be the transitional regime. And at higher flow rates, the turbulent regime will dominate, and the flow rate will add more resistance and therefore more friction because the velocity is greater, as previously stated. So here we can experimentally calculate the Reynolds number as either determining laminar or turbulent flow. So as I said, it's a non-dimensional number that relates density, velocity, and diameter to the viscosity of the fluid. So if the Reynolds number is less than 2,000, the flow will be laminar, and it will have the linear relationship as shown on the graph above. And if it's between 2,000 and 4,000, the flow will be transitional, so it will alternate between the laminar and turbulent flow regime and will be very unpredictable. And then when the Reynolds number is greater than 4,000, the flow will be turbulent, and the flow rate can also be proportional to the change in pressure, depending on if the pipe is rough or smooth. And this is, again, when the fluid tumbles back on itself and creates eddies as it flows through the pipe, increasing friction. So then for pipe flow, you can derive the derivation of the Reynolds number comes from using the Buckingham pi method, if you will, which gives certain different variables for each different non-dimensional numbers for pipe flow. So using this method, z is going to be 6 and y is going to be 3. And then we pick 3 variables of the 6. So z represents the number of variables and y represents the number of dimensions. So in this case, we have 6 variables, and the number of dimensions is 3 because what is used is kilograms, meters, and seconds in different ways. So we start by picking 3 variables, and I won't explain this entire process because that will lose focus on the Reynolds number. But essentially, you come up with 3 dimensionless numbers, which is the length of the pipe over the diameter, the change in pressure over the density times the velocity squared, and lastly, the Reynolds number, which is the viscosity in relationship to the diameter, the velocity, and the density of the pipe. And you'll come to find that the Reynolds number is a function of the other two non-dimensional numbers, but additionally, the other two non-dimensional numbers can all be related back to the Reynolds number. So that's essentially it. The takeaway should be that the Reynolds number determines laminar and turbulent flow based on these regions. And laminar and turbulent flow are important because they affect how heat and mass can be transferred within a pipe.